So, been through timber and steel, I think, sufficiently. What we haven't covered yet is termites. I'll see if we can weave a bit of that in toward the end of today's lesson, but the most important thing, I think, is to get going with concrete and footings and foundations. So we'll come back to that a little bit later. So concrete's one of those building materials that's been around for a long time, and it will continue to be used and used very broadly. It's one of the cheapest building materials you can use. Typically, well, yeah, it does make up a large part of your building cost, probably around the 15-20% of your total build cost. But per volume, it's actually quite cheap, around the $200 to $300 a cubic metre, depending on where you are in the state, and depending on what strength of concrete you're ordering as well. The thing with concrete is we typically tend to use it in very large volumes. But it's one of those materials that's been around for a very long time. For anybody who's travelled, around Europe extensively or so, you'd see Roman ruins several thousand years old, still quite solid. But the majority of use of concrete is used in footings, and that's what we're looking at with today's presentation. For our research report, we're comparing suspended lightweight floor framing systems with doing a concrete slab on ground. Whenever we do a concrete slab on ground, we want to employ an engineer for doing that. In fact, whenever we want to do footings, we'll have to employ an engineer for that. And also it's not just any engineer or any structural engineer for that matter, it's a structural engineer that has an insurance for footings as well. So not all structural engineers have insurance for footings. What they'll do is they'll compile the footing report. So typically the process goes that you have a site inspection, and then you contact the engineer saying, this is what we want to be doing in this location. So we'll get our site, have a bit of an idea of where we want to build the building like this, get that to the engineer and say, look, this is where we're looking to do the building. They'll come out and they'll get 4 logs done in several locations on the site. Typically cluster around 3 bore logs where you're going to do the house, and then if you're going to have an on-site wastewater system, they'll do another one to only about 1.5 metres elsewhere on the site where you're looking to do on-site wastewater system. So they'll take those soil samples to get an idea of what the soil is doing, because that's going to be your major driver in how strong your footings need to be and how much concrete is going to go in there. Once they've compiled their footings report, and you start construction, you bench the site, you take away all the humus layer, the layer of compactable material on the top of the soil, and then bring in some compactable rubble, typically to about 100 mil deep, but as per the engineer's report. Excavate for your footing beams, and then notify the engineer when you're doing that excavation. If things are going well, typically your engineer will want 48 hours notice before inspecting the footing excavation. They want to inspect that footing excavation because if they only come out to inspect the steel work later on and there's an issue with the footings, with the actual excavation, that's a very difficult and expensive thing to rectify. Then they'll probably want to come out to inspect the steel work as well that's gone in the footing trenches. And then after that's all passed inspection, then it can get covered with concrete. So, and we'll see a little bit more of this process as we work through today. So that's their engagement with the footings. You may also have an engineer design your roof trusses or other framing sections, portal frames, things like that. If you're getting some large steel sections into your frame, or you may, maybe the truss manufacturer that does the engineering for the trusses. Also, it's a very important thing typically to keep any retaining walls at less than a metre high, because if you go over a metre high, then it requires engineering for the retaining walls. So that's, well, you're typically looking at a bill of around $1,500 for engineering for retaining walls, plus engineered retaining walls are typically quite expensive to build as well. So if you keep your retaining walls down low, you keep your costs down a lot less with your retaining walls. And typically what the way an engineer works is to establish the worst case situation and design the building elements to resist that loading. There's a whole lot of loads that an engineer has to consider on a building. So all of the dead loads, which is just simply the weight of the building, everything that makes up that building fabric and isn't going to move. That also includes things like hot water services and air conditioners, things like that also impose a fair bit of weight, but aren't going to be taken in and out. They also have to design a building for live loads, for considering the weight of people moving into a room, grand pianos, all that sort of thing. Then wind loads, so the horizontal forces of wind and also the suction that creates on top of the building as it moves over. And then earthquake or snow loads in certain areas. We don't have to design for that. In South Australia, no snow and fairly stable. Covered this to a small extent last week, but we'll talk about it a little bit more. So, force is a push-pull action. Two major ways of looking at the forces, or the two forces impacting predominantly on building elements, are compression and tension, and you can see that in buildings everywhere, in just about any element of a building. Look at that and see what aspects are in compression and what sections are in tension. With that compression and tension, typically if we want to make say a joist, something that spans from distance to distance. This knife is not working that well. If we want to get something to span a long distance, the important thing is to make that element deep, because that means that the amount of compression and tension resisted is further, right at the centre here. Our compression and our tension are neutral. Right in the centre of the beam, they're neutral. The further we get our material away from that neutral point, and the more material we have at those points, the more compression and tension it resists. So if I get, say, this plank like this, and I lay that across two things, point of support, if I stand on that, or if I jump on that, I might be able to snap it. But if I turn it up this way, like that, and retain it at the ends to stop it from rolling, I'll have a really hard time snapping it, because it's deeper in this section than it is through that section. There are also shear forces which are happening as well, which are where we have two forces acting against each other in very close proximity, so with very little eccentricity. If we've got a force happening down and a force happening up, say separated by a metre or so, there's a lot of eccentricity in that. Those forces are a long way apart from each other and they'll tend to rotate something. But if that force is happening, you've got a force down and a force up very close to each other, then they tend to shear materials. One of the things you see a lot, well, quite often with buildings in reactive areas, you get stepped cracking through the brickwork. Has anybody ever seen that before? Like, it follows the line of mortar. that's typically not indicative of as bad a problem as when you get cracking that goes straight up and it goes straight through brickwork. Because when you've got cracking that's going straight up through brickwork, you know you've got forces acting in a very localized way, and typically those forces are far more destructive than forces spread out over a larger area, which gives you that oblique stepped cracking. Typically, those forces are expressed visually in deflection. Now, deflection's not always an issue. We can get like a steel I-beam, for example, to deflect a long way before it fails, but it's not aesthetically pleasing. It's not something we want to see in buildings. Beyond the aesthetics, we don't want elements to go deflecting where they will go imposing loads on other materials, such as windows, for example. If we had something deflecting over top of those windows there like that, then that would crack those windows and it would be permanently imposing forces on those windows. So you have to allow for some deflection in building materials. So with your roof framing, where you've got pitching beams and counter beams, strutting beams, etc., those beams have to have a gap underneath them between any other element beneath them to allow them to deflect ever so slightly without imposing a load on something else. Also with lintels above openings in framing, you want to have that lintel have a little bit of a gap between that and your door or your window to allow a small amount of deflection in that lintel without imposing a load on any of your framing around it. So we have to allow small gaps, etc., for deflection. Deflection happens. Typically, we hide it within roofs and walls, but we have to consider that, particularly if it's above windows. 10 points for anybody who can give me the difference between foundation and footing. No, okay, lots of street cred for someone who can give me the difference between foundation and footing. No?
Isn't foundation like on the ground and footings are coming out of the ground?
Kind of, yeah. So foundation is actually what we build upon. So
a little bit off.
Yeah, a little bit off. Yeah. So foundation is the stuff in the ground.
Yeah. Like
Whereas
pipes and stuff, right?
no. It's like so foundation might be just the soil, the natural soil that's there, or the compactable rubble or something that we bring in to the site. It's whatever we end up building on top of. So
is that what we compact down?
Yes.
Foundation?
No. So we do the footings off. Yeah. And that's why I'm sort of hammering this definition a bit, because quite often you watch Renault shows or something like that on TV, and that terminology gets mixed up all the time between foundations and footings. They'll say, oh, the foundations are cracking, or it's actually the footings that are cracking because the foundations are moving. So foundation is the rock or soil in its natural state on a building site. Or actually, natural or improved state. It's what we end up building on top of. And the footing is the lowest element of the structure in contact with the ground. And so it distributes the total load of the building. Yeah, typically it's going to be concrete. You're not going to... you can do footings from other things. You can drive steel pylons into the ground. You can drive permafine posts into the ground. But typically, right, it's going to be your concrete. So lots of different types of footings. We've got integrated. That's where you've got beams tied together with a slab on top, and the whole thing moves as one. You've got continuous footings, which is a strip footing or a beam footing. We don't typically use those in South Australia because our soil is too reactive for that type of footing, but we might use that sort of footing for a wall, like an isolated wall that's not going to have a house built on top of it. Or you might do isolated pads and piers. So in fairly stable locations, if we're doing an elevated floor, you'll do pads or piers. So I mentioned before, one of the first steps we do is get soil samples done. Typically, your larger engineering firms will have an in-house soil sampling, how to say it, well, department. So the engineers that I use, they also own a soil sampling business as well. So it's all the one package, and they can rely on those soil samples. But you don't always have to go with that. You can have independent soil samplers come out and do your assessment. You might even want to get if you're looking at buying land or advising people to buy land, etc. You may want to get those soil samples done initially. Typically, it costs around that $500 mark to get those soil samples done, which may be a very worthwhile investment because there can be, even for a small house, there can be about $20,000 difference between clay soil or reasonably stable loam. So that $500 can be money well spent in some scenarios. So the different types of soils we end up looking at. So we've got stable soils, which exhibit little movement and provide a very stable base. Reactive soils that react with moisture, and they swell as moisture content increases and shrinks as it dries out. Has anybody, you probably would have seen where you've got clay soils and it's dried out and you get this cracking in the ground and gaps opening up. Has anybody seen that in the parklands around the city?
Yesterday, it was on somebody's front yard.
Yep.
Massive cracks.
Yep. Yeah. Absolute massive cracks around at the moment because our soils are drying out probably more than I've ever seen before, because it's been a really long time since we've had any decent sort of rain. So we've got massive cracks opening up around the place. So this is typically the soil that we're dealing with in Adelaide and what causes most of the problems. However, there are some soft, highly compressible soils that are unable to support loads. So down around the Port Adelaide area, Rosewater area, you've got some soft, really silty soils with a lot of organic matter in them, deposited soils that are compressible. And then in some areas, but not in many areas, we've got collapsing soils. So collapsing soils, typically soils that have been windborne sand. So sand has been deposited by wind, sand dunes, that type of thing, or sand that gets moved around. And then those sand particles, quite large and jagged, well, in terms of pieces of soil, right? Not large in terms of something to look at, but quite jagged. This is like your clay, like that. This is your sand, larger pieces like that don't fit together well. But when you add water to that, it lubricates them and they start fitting together better. So you can get sand, you can wet it down, and you can watch it collapse. That's something that builders have to be aware of as well. So I had a building out of Renmark that had a broken down pipe that continuously poured water onto a section near the building, and that caused that soil to collapse underneath that. But that's not a very typical thing. So, as I mentioned before, you might want to get a soil sample done before the purchase of land. So that's a preliminary sample. Or once you've decided where the house is going to go, then you get a construction report done. So it details the footing type, site works. That's based on the bore log. The engineer will at that stage want a site plan. It's better if you can supply them with a site plan than have them draw it up themselves. And that will want to have the contours on it. And then from that, now either you or the engineer will determine the cut and fill information from that. And typically within your engineering report, there'll be some paving advice as well. I'll just have a quick look on my...
Typically it's 3 bore logs, yeah?
Typically it's 3, yeah. But you may need to get more, or you may be allowed to get away with less. So you're allowed to do less when you're working on a larger subdivision and the bore logs are very uniform across those samples. So then when you've got a lot of uniformity across, then you're allowed to reduce it to one bore log, one soil sample per allotment. But typically it's going to be 3 on the allotment. No, I don't. No, actually, yeah. I was going to see if I've got a complete engineering report for footings that we can just have a really quick look at, because it's an interesting thing to have a look at. So what have we got? Yeah. This is not an entire one. So what have we got to look at that? So this is a bore log there, showing the boreholes and the depth of those boreholes and the depth of the horizons of soil that it goes through. And we've got some bore logs here in the slides, so I won't spend too much time looking at those. That's typically your footing plan that will come through. I'll rotate. Right. So that details where your footing beams are going to go, and then the slab above that. And on this page is where the majority of your information comes. So we've got an E next to all these beams. That denotes them as an external beam. And then we have a look on the table here. That external beam is going to be 300 wide by 1150 deep, which is a very deep footing. And then once we get really deep like that, we have to put a lot of steel in there. So this one's got 6 N20 bars, 3 top and 3 bottom in our beam. And that'll make a bit more sense as we move through. And then this denotes our ligatures. So I'll talk about those reinforcing cages. So typically this page gives you pretty much all the information you need in regards to construction of those footings. So that's the page that will go to your excavator driver, the people doing the site works and the steel fixing, and also to the concreter. And I've just taken little bits out of an engineering report to summarise it for this, so I don't have the full report here with me. But typically, yeah, your report's going to be around that sort of 30 pages or so, and it's going to include a whole lot of details in regards to how you deal with certain aspects. So you've got some paving advice here and the height of paving and slope of paving away from the building. You've got advice on how you deal with set downs with your reinforcing and your ligatures, where to be placing your internal steelwork, so your slab mesh, and then where to be placing vapor barrier and compacted fill. So it tells us here 100 millimeters minimum compacted granular fill underneath that. So you typically have all of this information within your engineering report. This is detailing to what extent you can excavate next to a footing beam. So to what depth. So yeah, that one gives how much lap you have to have of your slab mesh within any set downs. So that's an important detail for determining how much slab mesh you need, and also what you have to do with the excavation. So when you're excavating on site, you have to cut this soil away deeper. So that's some little snippets out of an engineering report. The reason that that the engineers will include things like paving advice around your footings is because that impacts the amount of moisture that's going to be gathering around your footings. And if we've got soils that swell or contract with a lot of moisture, then we want to reduce the amount of moisture or rain that soaks into the ground near our footings. So we need to have 50 millimetres of fall for the first metre of our paving to ensure the water moves away from the site. Okay. So various different methods of soil sampling. Typically your most common is going to be a push tube. And yeah, by and large, soil samples are going to be done by a full drive, like a Land Cruiser ute with a push tube on the back of it, hydraulically driven, and you're going to get that ute in there, and then push the tube down and pull it out, and you bring out a core sample like this of your soil. Sometimes access is really tight, and you get like a little dingo digger in there doing the push tube, ramming that down, or even hand-driven push tubes at times. I've even seen soil samples done inside hallways, inside the hallway of a house. So take up the floorboards and do a soil sample inside the house. So you can do soil samples pretty much anywhere, but it's certainly much easier if you can just drive in there and use the push tube on the back of the ute. So the main thing we get from our soil samples, well, it's that classification of the site, and we get our Y value. Do I still have that? I think on this engineering report, right at the start, there we had, I think it was a Y value of around, yeah. So this class ED site with Y values approximately 110 millimetres. Now that's really quite extreme. That's why those footing beams are 1150 deep, because we can expect 110 millimetres absolute maximum movement between when the soil is completely dry and when it swells with moisture. So 110 millimetres, that's a bit taller than this marker pen. That's probably about 90 mil. So yeah, 110 millimetres of movement. That's how much that building could potentially move on the site, up and down. So that Y value is defined as the movement at ground surface level during the life expectancy of the building. So yeah, our extremely reactive, that's when you've got Y values over 100. Highly reactive, I think it's Y values over 70. Moderately between 20 and 70, I'm not sure, and stable below that. So I showed you that bore log just quickly earlier on that was tilted on its side. This is one that's a bit friendlier to read. So what we can see in this bore log is that we've got 3 boreholes which were done. So we've got borehole 1, borehole 2, borehole 3, and that should always be read in conjunction with a site plan. So that site plan shows that where borehole 1, borehole 2, and borehole 3 were located, because that helps us build up that picture. So we've got 3 boreholes done there, and then we can see the total depth of those 3 boreholes by looking right down at the base of the table, and we can see that they are all 3 metres deep. So they went straight to 3 metres. A borehole will not always go entirely to 3 metres, and sometimes engineers will specify deeper boreholes. In our office, I think we typically went to 4 metre boreholes, because what we have in South Australia are what are called deep-seated clays, which mean we've got clay to a very to quite a depth, and you can get small amounts of movement even at 4 metres deep, because you've got moisture percolating through to that depth. So in certain situations you can have impacts on the top of your soil happening from about 4 metres down. So the minimum you have to go to is 3 metres, but sometimes engineers will want those taken to 4 metres or so. But at other times you hit rock, and when you hit rock, you can't go any further, obviously, with a push tube. So that's the end of it, and that's what's called refusal. So you'll do a borehole, and then you get to a couple metres or so, and you say, oh, we can't push through that rock, so refusal at 2 metres. And so then your mapping of your horizons within your bore log will stop at that 2 metres. So this push tube made it all the way to 3 metres for each of the soil samples, or for each of their holes. Then after that push tube is taken out, so what you do is, so you drive it down a metre, and then you twist it and screw another one on, drive that down, screw another one on, and keep driving it down until you've got 3 of them down in the ground, and then you pull them up and reverse the process. So unscrew one, and you tap the soil out into a tray, so you can see what's happening in all of those layers, and inspect each of those layers. And you'll typically get very clear horizons happening. So with our soil, we've got, typically soil gets deposited over, hundreds of thousands, millions of years in different layers, and you've got different characteristics in different layers, and that's what are called horizons. So if we can see, well, that's probably not a distinct horizon. That's probably one that's been sitting in that tray a little bit longer than this one. This one's probably just freshly come out, got a lot of moisture it's losing. But yeah, down there we can see some clear horizons in that soil there. Or for anybody who visit the southern beaches, Port Wollonga or something like that, in the cliffs there you can see all the horizons of the soil, and see that soil changing as you pass through. So in this soil here, we can see we've got the humus layer right at the top. So for the first 250 mil or so, we've got humus, and then we've got a loam, like a fairly nice sort of friable loam with a bit of weathered rock in there. Then underneath that, it looks to be a white clay, with also weathered rock fragments going into a brown clay underneath that. So we've got our different horizons happening here. So one horizon up here, another horizon there, another horizon about there, another horizon approximately there. And that's what gets reflected in our bore logs. So we can see those different horizons of soil, and then it's determined by the soil sampler or the engineer inspecting how much movement we can expect from drying to saturation of that soil. So sandy soils won't move very much at all with drying to saturation, whereas clay soils will move a lot, and it's that percentage of clay within the soil that will determine how much movement. The other important thing to note from our soil samples is not only expected movement at surface level, but how much strength that soil has as well. Some soils don't have a lot of bearing capacity. I can't remember what the cutoff. So in AS2870, so that's the Australian standard for residential slabs footings. I think it's like 110 kPa or so bearing capacity your soil has to have. So that's a moderately loamy, clayey sort of soil. Some soils will not have that bearing capacity and need to be improved by bringing in compactable rubble, etc. But that's the other aspect your engineer is going to be looking at, is that bearing capacity of the soil, how much weight that soil can take before pushing out of the way. So once it's determined what type of soil makes up your foundation, then the footings can be designed, and there's decisions made on what type of footings. Typically within South Australia, because we have a lot of reactive clays throughout the metropolitan area, we go with a slab on ground and a raft slab at that. The reason it's called a raft slab is because it's designed to carry the whole of the building, and that soil can move around underneath, and that slab will move with that soil and will carry the whole building. So that slab is designed to be able to take that weight and to not crack, and to allow that movement. One thing I used to do a lot of is take a laser level and go around the edge of a building to work out how much they're moving around. Typically, the worst place I've seen is 150 millimeters of slope from one side of the building to the other. So that's about 2 bricks worth. So that's typically about the worst you'll get in Adelaide, or the worst I've seen, where you might get some saturation on one side, where you've got a broken down pipe, something like that, saturating soil, and then on the other side you've got a tree, like a big gum tree. Eucalypts are fantastic at pumping water out of soil, and so that's about typically the worst amount of movement you'll see. But I've seen situations whereby buildings slope 150 millimeters from one side to the other, but exhibit very little cracking, and then in other instances only had about 20 millimeters of variation, but had significant cracking. The difference between those is the distribution of forces across the building. If we've got a building that, or got a foundation which is slowly drying on one side and increasing in moisture on the other side, and those two forces are a long way apart and quite even between them, we won't see much cracking in the building. But if we've got a broken pipe right in the centre of the building, which is causing heave in a very localised fashion, then we might not get actually much movement of the building, but significant cracking. So that's another thing that engineers are going to be looking for in those bore logs or those soil samples, is the uniformity across those bore logs. So these are our Y values expressed down here from each borehole. That's pretty good. That's not extremely reactive soil. Sort of, it's moderate to high reactive. Hole 1 and hole 2, 54 and 56. Our Y values very similar, and then 65. So that's about 20% difference. It's not a huge difference. You wouldn't have to design really intense footings for that type of building. It also depends on what sort of weight is going on there, but there's a lot of uniformity in those Y values. If I had a Y value of 54, 56, and then 20, that would probably be just, if not more, concerning, because then we can see that there's the potential for a lot of movement in one area, but little potential for movement in another area, if that Y value is extremely low. So it's not just the total number you're looking at, but also the difference between the two. So those slab on that raft slab, that helps carry the building no matter what the soil is doing. Beyond that, if we've got quite problematic soil, like in places around toward Port Adelaide, from Bowden, Brompton area through to Port Adelaide, there were clay pits dug out for manufacturing bricks. And then those pits have been filled in with all sorts of stuff, car bodies, whatever. Those are particularly problematic sites to build on, because all the stuff that was chucked in there gets compressible after time. And so if you're going to be doing a footing on top of that, you want to bypass all of that junk and get into solid ground underneath. One way of getting into solid ground underneath is to auger piers. So you get a large auger. Did anybody see any of the work that was going on around? Yeah, I don't think there's any augers happening around here, but there's when all this Southern Expressway stuff was, the bypass there was being built, a lot of really big machines called continuous flight auger, a CFA, that I don't know, sort of 20 metres high or so, augering piers down into the ground. So anyhow, that's typically what you do. You have a really long auger, and that will take out a tube of soil, and then then you make up a reinforcing cage that goes down in there, and that gets filled with concrete to make a concrete pier going all the way down to lock into stable soil down underneath. So that's how you bypass all the junk that's deposited on the top.
So it's like a big drill.
A big drill, like a giant drill for in the earth. And then you do your slab on top of that, or you may do so this is a bridge construction, but technically it's the same same concept, in that you've got a pier, so that will be augered down into the ground, and then a beam on top of that, and then you do a slab on top of that. So that may happen above ground, or all of that may happen that may be happening below the ground if we've got very poor foundation underneath. So that's pier and slab. Well, that's pier and beam and pier and slab essentially. One South Australian invention for raft slabs is what's called a waffle pod slab. Those waffle pod slabs can only be used on sites with Y values up to 80, so not extremely highly reactive, but there's still plenty of sites, around Adelaide metropolitan area that are 80 or below. Rather than excavate big trenches in the ground and put steel reinforcing cages in those trenches and fill those with concrete, with the waffle pod system, what you do is you flatten out the ground and you put your compactable rubble on the top, and then you put out your styrofoam blocks with spaces between them, lay the steel in between those, and then pour the concrete on that, which means you end up having a slab which is 400 millimetres above the ground, which is very handy in places like Lewiston and Two Wells where they get flooding. But you pick so you've got a slab that's about 400 millimetres above ground, and it sits on top of that ground. This is basically what it looks like from underneath. So you get a series of styrofoam boxes that create those voids and end up vicariously producing your beams. Beyond that, another type of slab system which is used a lot by volume builders, so builders who are doing many projects, is the grillage raft slab. The reason you'd use a grillage raft slab is because you want to have deeper beams, but also it makes the steel fixing much quicker and simpler. With your typical raft slab, to do a cross section through that, as we saw on that engineering report, I'll scroll down to detail. We see that the reinforcing is placed inside those footing beams with 3 bars on the top, 3 bars on the bottom, and ligatures that hold them into a cage. I don't have a cross-section through a grillage raft here, but a grillage raft instead will have, so these are 20 mil bars for this project, but a grillage raft might have 32 mil bars, so really fat bars, but only have 1 at the top and 1 at the bottom. So it makes it so much simpler for placing that steel and fixing it, because you just have 1 bar and then a hanger from that, and then you have your other bar dropped in the bottom of that. So the steel fixing for a grillage raft is really quick and simple. And so a lot of your volume builders prefer to use that system. The downfall of using a grillage raft is that you don't get quite as much even distribution of forces through your footing. So you probably don't want to be going to do that if you're going to have an exposed concrete surface, or if you're going to be doing polished concrete surface, because there's more likelihood of cracking happening in your slab. So a bit of cracking is not always an issue. So there's the Australian standard for slabs and footings allows 5mm cracks, which I think is really quite extreme. But there is some allowance for cracking in concrete, and cracking is almost unavoidable. But there are some things you can do to minimise that. And one of those ways is the traditional raft slab as opposed to the grillage raft. Beyond the grillage raft, there's also stripped footings. So if anybody's lived in an old cottage in sort of the eastern areas of Adelaide, sort of Unley Parkside sort of region, you'll notice that there's a lot of cracking that happens in those buildings. It's not because the soil there, like the soil is bad there, but it's not as bad as it is in Keswick or Newton or Ross Trevor. The reason those buildings crack a lot around there is because they were built before the invention of the raft slab, and they typically had strip footings underneath, which aren't strong enough to resist the forces in our soil around Adelaide. So I'll go through the construction process for our raft slab, and then I'll progress through the others fairly quickly. So for the stiffened raft, first thing you do is clear the site. Typically, you're going to be removing 150 millimeters of topsoil, but what you're going to do is, you never really know what you've got under the ground until you start digging it away. The place where we're building at the moment, I thought the topsoil typically was going to be around the 300 mil, and we'll be removing 300 mil. In places, we're removing up to about 800 mil before we started getting black humusy soil out. And you see, just it was in dips, etc. So I guess that was a kind of fairly good case scenario there, because there's lots of fantastic topsoil and very little rubbish soil to get rid of. But you never really know until you start excavating. Typically, it's only going to be around that 150 millimeter layer that has humus in it. So humus, that's all your broken down grass and leaves, all the organic matter. The reason you want to remove that is because that's quite compressible. If you leave that on the ground and you put a building on top of that, it squashes down and can't bear load. And it's also, you don't want to get rid of it. You want to take that away and you want to put that up the back of the block or wherever you're going to be doing garden beds, because it's fantastic stuff for growing and takes thousands of years to produce. So you take away that top layer of soil, and you do that to a metre around where you're going to be working. Typically, what you want to be doing is giving yourself about a metre of having a flat section around your slab, because you're going to be doing paving, etc. And it's so much easier to go excavating and cutting things flat when you've got a vacant site than when you've got a slab in the way. Then you'll typically bring in about 100 millimeters depth of compactable fill and create that building pad to a metre past where your edge of your footing beams are going to be. And then you compact it and roll it in in maximum 150 mil layers. So if there are areas that you have to build it up a lot more, you have to get a lot more depth, we'll then lay it in maximum 150, wet it and compact it. Once you've got that flat site, and that's a fairly messy looking one. I'd probably like it to be a bit smoother than that before you start marking out. But once that's all screeded off, really nice and flat. And also bear in mind, the flatter and the smoother you get it, the less concrete you use. And when you're going to have a concrete bill of around that $20,000 or so, 10% extra can be a fair bit of money. So it's worth that time getting your bench really nice and flat. So that's an extremely good example. You typically won't get footing beams cut in that nicely, but that shows that 100 millimeters of compactable rubble on the top, or quarry sand, and then a 45 mil cutaway for the edge as well. That helps give the interaction between your footing beams and your slab extra strength right in that corner there. Breakaways like this are pretty much always going to happen. So that's a really good example. You'll very rarely see footing excavation as neat as that, and that's typically a bit more what you want to see. Well, that's on the rough side of things, I think. Anyhow, so you've benched your site, and then you set out string lines. I think I mentioned last week 3-4-5 triangle. Does everybody remember the 3-4-5 triangle? Yeah. So that's how you do it. So you work out where definitively where one side of the building is going to go. So you measure that off the boundary from your site plan. Get that one string line in place, and then set out all your other string lines from that using 3-4-5 triangle. Then do the check method corner to corner, and if they all match up, that's it. So once again, incredibly important to spend time on that process, or have your builders and concreters spending time on that process to get it perfect. Yes, so concrete will end up going on top of this. So basically what that soil or what that foundation ends up being, that ends up being the formwork for the concrete to go over top of. If we, let's say for example we didn't cut in footing beams like this and we did just a flat slab, that slab wouldn't have that strength to resist forces picking it up from side to side. As I expressed with this before, the greater the depth we give something, the more strength we give it. So if we have a slab and we excavate for beams like that and then fill those full of concrete, that gives our slab a great deal more strength to resist forces of heave and subsidence. So you do the set out and you mark it out, and then the excavator driver cuts out all your footing beams. Then for wherever you've got wet areas, typically you'll set a wet area down by 50 millimeters. The reason you set a wet area down by 50 millimeters is because you want your tiles to slope to your drains, and that's not an easy or accurate thing to get concreters to do on site. So what you do is you drop that floor level by about 50 millimeters to enable you to then put in a cementitious screed later on, and then do the falls correctly with the cementitious screed straight to the outlets. Because we're stepping our wet areas down, because we want that slope in the tiling, then our top layer here has to be set down by 50 millimeters, which means that when we're excavating the soil before we do the compactable rubble, we have to excavate that section down by 50 millimeters to ensure that we've got 100 mil topping in both areas. Does that make sense, everyone? So that process has to be fairly well planned out. Then once that excavation is going well, you'll probably, before the excavation is finished, you'll probably get onto your engineer and email the inspections department and say, yeah, we want to book in an inspection for tomorrow morning, tomorrow evening, etc. And then the engineer will come out and inspect at this stage. So they'll come around and they'll measure the depth of trenches, the width of trenches, they'll tell you to clean them out, etc. And then give their report, the go ahead for fixing the steel. Whilst you're waiting for your engineer to arrive, you get your first fix plumbing in. So before we go putting any of the steel work in, you want to put all your pipes in and then backfill over where those pipes are. So that's a fairly rough job there. I think that would have been fairly clayish soil because you got your beams really close together. Would have been a very difficult one to excavate for, and then with all that footing, with all that plumbing in there, fairly difficult one to do. Anyhow, what you'll notice on this first fix plumbing is that there's this spongy rubber that's taped around all of those pipes. Wherever you have pipes which go through a footing beam, you need to put a layer of that lagging around it. Now, if it's moderately reactive soil, you do one layer of lagging. If it's highly reactive or extremely reactive, you do 2 layers of lagging around it. That's basically the shock absorber for when soil moves, different to footings. Because if we've got soil that's getting saturated and it's expanding, typically that's going to push past the footing beams. It'll try to lift the footings up a little bit, but because there's a lot of weight and all of that, it'll push past them and it will try to lift the plumbing up as it goes. Therefore, if we do lagging around the pipes, then that allows some movement in there because we don't have concrete around the pipe. But it's things like this that are very important to look out for. So what's happened here is the plumber has lagged all of that, and that's all been lagged correctly. But as soon as you go putting concrete in here, concrete is going to bind around that pipe there, that section there, and that's not lagged. So what I'd like to see is that lagging carried around that and that packed out, or possibly you get a piece of ply in there and pack soil again. to make sure that you don't get concrete binding around your pipes. Because as soon as you get concrete binding around your pipes, the rest of that lagging is pretty much useless. Because your pipe is held into that footing beam, and if you get differential movement with your slab, then you can crack pipes. And cracking pipes under a slab is, well, it's not a, it's a very difficult process, a very difficult thing to rectify. You can go sleeving pipes, you can go cutting through slabs, etc., to repair pipes, but it's not a good or cheap job to do. So, yeah, just those small details can be very important. If that's on the inside of your slab, typically that's going to be less problematic than if it's on the outside of your slab, because you get more differential movement on the outside. But because I've got pipes coming out here, I imagine that this is, yeah, well, this one may be the external one. Anyhow, it's those details to look out for. Following that, then for all residential slabs, you have to have plastic underneath to stop that moisture egress through the slab. So that 0.2 mil polythene layer gets put down, and that's a fairly important bit to get right as well. So that you want done very neatly, and you want adequate plastic in those trenches, of course. So plastic goes down, and then the steel fixing happens for all of your beams in between. So make that a little bit. So we've got another. Yeah, that's a better one there. So what we can see there is we've got 3 bars at the top, and then we'll have 3 bars at the bottom of that beam as well. Those ones, yeah, probably like 18 mil bars or so. What you want to see is all of those bars lapping correctly. You want them coming right to the corner. If you don't have bars which come all the way to the corner, then that's a very vulnerable position for that to crack and to open up when stresses are placed on that. So those bars end up being held together in big cages made up by these ligatures. And so the engineer will want to come out and inspect at that stage as well, because they want to ensure that all of that steel work has gone in correctly. So typically the way it happens is those large cages are made up next to the slab and then carried in and dropped in. When you've got plumbing penetrating through, you have to lay the bars down underneath and then tie your ligatures, have them sitting up and tie it up high, and then tie your bars in there and then drop them down. After that's all in place, then you put out all the slab mesh. So these bars here resist a lot of your forces of heave and subsidence, whereas this slab mesh, that helps control cracking in your slab surface. If you've got some soft fill underneath, or more than 300 millimeters of uncontrolled fill, well, then you need to do 2 layers of mesh. So 1 layer of SL72, 1 layer of SL92. With your mesh, that's just for square mesh, and or SL72 is 7 mil bars at 200 centers. Can anybody think what SL92 would be? Yeah, well, SL82 is 8 mil bars at 200 centers.
Oh, 9 mil bars.
9 mil bars at 200 centers. Yeah. So there's actually a fair bit of steel that goes into like SL92, and you get, yeah, and then also you got mesh, which is 10 mil bars at 100 mil centers as well. So if you're doing a wind farm or something like that. So that slab mesh goes on the top, and the reason we've got 2 different chairs is because one layer is held down low in the slab, the other layer is held up high. So these will be set at about 90 millimeters, and those be set at 40 millimeters. A very important thing with the concrete or with the steel work is you get adequate concrete coverage. So the minimum cover to the top of any steel work inside the building to a protected area is 25 millimeters. Now, one quirk of this building is that if you walk around having a look at the concrete in some sections here, you can actually see some of that reinforcing really close to the surface. In fact, some of it's right on the surface. So have a look for that here. I don't know what went wrong with the construction of this. Some bits in here, but that's important to minimise, because if you don't have adequate concrete coverage, that steel will rust, and as it rusts, it expands and pushes concrete away from the steel work, which means it rusts even more, which means it expands more and pops concrete away. So 25 millimeters to any to the inside of buildings, to any protected surface, and then 40 millimeters to the sides and bottoms of your beams. At this point in time, you also have to think about termite protection as well. So while you're waiting for your engineer to come out and inspect the steelwork, you can get like Termimesh, or what are they called, cordon, in to install small sections around all of your pipes. So your concrete slab is considered to be an effective deterrent against termites because they can't get through that slab. But because concrete shrinks as it's going off, it shrinks away from pipes and leaves a gap next to those pipes. So you get, so this is an example of Termimesh. So Termimesh are an Adelaide company. They'll come and put a stainless steel skirt around all of your plumbing penetrations, so that when that concrete shrinks away from that, it doesn't leave a gap that termites can come in through. So cordon do basically the same thing. Cordon barrier looks a lot like your orange plastic, but what it is, it's orange plastic with termite poison, like a layer of termite poison, then another layer of orange plastic again. So it's this termite poison sandwich, and that gets put around your pipes as well. So that, because once again, termites try to eat their way through it, they get poisoned. So that's a chemical-free way, and cordon uses chemicals. Another way is you can spray down the site, prior to laying a slab, or the NCC. In terms of termites, it allows for no termite protection if the primary building elements cannot be eaten by the termites, if they're not a food source for the termites. So that might be that all your structural elements are made up of termite protected timber, so your blue or green timber, or it might be that it's steel frame. So that's the example of, well, that's once again the NCC, how it's the worst possible building that can legally be built. You can get away with not doing termite protection in those instances, but still you're going to have timber architraves and grand pianos and all that sort of stuff that termites will want to eat. So although you can do that, I still suggest, it's typically less than $200 to get the all your penetrations sealed up. Even if the NCC doesn't say that you have to, because your primary building elements are steel also. Here's more instances of steel work. So these are fairly solid bars, 20 mil bars or so. That's some pretty intense reinforcing there. We've got ligatures that are stepped. That's for a rebate. So stepped ligatures for a rebate happening there. That's a fairly typical completed one. So that's that cordon barrier that I was talking about. Also, a very important thing is cap all your pipes with tape as well. You don't want to get any concrete in those. And another handy thing is, some plumbers will use plugs on the end of those pipes. So they'll put the pipes in, and those pipes won't be carried anywhere just yet. And they'll just plug the end of those pipes and then fill them up with water. And that way, they know that when the steel fixing happens, because the steel fixes can be quite rough with plumbing, if they're too rough, you'll get water pouring out at that point, telling you that the pipes have been broken, and you can repair all that before any concrete goes in there. So after all that steelwork's in place, the engineers come out, inspected it, and said, yes, it's all fine, everything's working fine, you've got adequate coverage, etc. Then the concreters will come in and do the concreting. You might use timber or steel forms. That's up to the concreters, and they may form it up beforehand, or they may form it up while they're pouring it as well. So typically, with a lot of slabs, concreters will actually be doing, well, they'll have their pins and things in place, but then they'll actually be forming that up as they go along. Though if you're using timber forms, they're oiled to allow for separation, so they don't go sticking to the concrete afterwards. Very important is that they're placed and staked adequately to allow, or to ensure there's no overturning while the concrete is being placed. The concrete pours are pretty hectic and very busy. You don't want any problems with that. Before you go placing the concrete, you have to give council at least 1 day's notice, so they can come out and do an inspection as well. They may or may not come out to inspect. On the day of the pour, it happens as a continual process, and look, that's up to the concreters to organise. A better concreter will have trucks arriving at just the right time and ordering just the right amount of concrete as well, because what you want is all of your concrete arriving back to back like that, so you don't have sections going dry and having cold formed joints and things like that in your concrete. They'll pour the wet areas first. So typically you use so this is a concrete pump here with a hopper on the back. And this one's a line pump. So you've got a line coming off the back of that, and that gets moved around and the concrete gets placed with that. Beyond simple line, so line pumps typically much cheaper to hire, but a lot more work. Whereas a boom pump, do I have a boom pump picture? No, I don't have a boom pump picture. Has anybody seen big concrete pumps with a really big arm coming off of that and a hose hanging from it yet? Yeah. So that's a boom pump. A little bit more expensive, but much easier for placing the concrete, because that boom can be operated by the concrete pumper who's out on the slab and just move that around. Anyhow, typically that's the mainstay of placing concrete now. People rarely use wheelbarrows for moving concrete around. You typically have a concrete pump come out. Concrete pump's going to cost close to $2,000, but it's going to make that process really quick and continuous. And also your pump operators are incredibly important people in that concreting process as well. They'll be doing actually a lot of the work of placing the concrete and compacting it, vibrating it into position. So that concrete goes in, and you want that to happen as a very continuous process. You don't want any breaks in that, and that comes down to the timing of all your trucks. Once the wet areas are done, once the beams are done and your wet areas, then you start doing the top. The process of doing the top is, when that concrete's going in, so this is the concrete coming out of the line pump, it gets vibrated into place. So you typically have one or two of the concreters going around with a two-stroke motor and a plunge vibrator that goes down into the concrete and brings up all the air bubbles. So they want to avoid hitting any of the steel work with it, because when you hit the steel work with it, it moves all the aggregate away out of the concrete. So you just want to be plunging that in until your air bubbles stop coming up to the surface, and just keep moving that around. Then once all the beams are poured like that, then the slab goes on top. Then once the slab's placed, so your concrete will want to know what sort of surface is going onto that concrete, what the purpose of that is, and they'll want to know that probably prior to even quoting on the job. If it's going to be a tiled surface, you want it to be reasonably smooth, but still have a bit of roughness to enable a little bit of grab for your screed that goes on top. You don't want lumps and chunks sticking up because that's going to compromise your waterproofing. You want it to be, you don't want it to be steel troweled smooth either. For carpet, it's going to be the same sort of thing. But if you're going to be doing an exposed finish, a burnish finish, well then you want that concrete to be really smooth on top. So you want a steel trowel to achieve that. One way of doing that is that's typically what you use on a residential slab, the helicopter. But for large industrial projects, you use one of these ride-on troweling machines that get a really smooth surface to it. And you'll notice the concrete is get on that concrete really early. So as soon as you can walk on it is when it will start getting troweled off. Also, if you're going to do polished concrete, you want the top of that concrete actually a little bit rough. The reason you want the concrete a little bit rough is because the diamond bits for cutting back the concrete actually grab on and do the cutting better if it's slightly rough. If you do a steel trowel finish, it's going to be really hard to cut it back. So the process of getting that surface on there, so once the concrete is placed, then it's bull floated. So you'll run a large screed, like a large flat bar across the top, and move that. Let's say we're moving our screed from this side of the room through to the other side of the room, getting it nice and flat. And then the next thing to come along is the bull float, which is a really large steel float on a long pole, which you do in an opposite direction to the way you screed. So you screed in one direction, then you bull float in the other direction. That gets it really smooth, and then you steel trowel after that. I'll just quickly get an image of a bull float there as well. So. So after the screeding, then you run a bull float over it, and then you trowel off after that. If we're doing paving or something, we might put an even rougher surface on top of that concrete by using a broom. So use a stiff bristle broom and run that across the top to roughen up the surface. So this shows where the wet areas are being set down. So you pour the concrete into the footing beams, and then you pour the wet area. And once that wet area, that level is all correct, then you set out your timber work, and then you pour around that. One really good detail, if you can achieve it on site, is to actually make up a timber frame the right size for that wet area before the concreting happens. That's all braced nicely, so you don't have to use these steel pins. The reason you don't want to use those steel pins is because those steel pins hold those boards in place while you're pouring the rest of it, but then they get pulled out and you fill that bit with concrete, but quite often you get differential cracking in that little bit there, which is an entry place for termites. So that's very common practice, but it's not the best practice. Best practice is to actually have a box made up for your set downs. So the set down gets created first, and those timbers will be 50 millimeters high, and then you'll pour the rest of your concrete up to the height of those boards. So that'll be the rest of your floor. So that's the finished product there, where you've got the top of your slab and your set down there, and then a further set down for the shower. So this set down might be 30 millimeters, and that might be 50 millimeters, or we might set the whole thing down by 50 millimeters.
Another thing you can do with your slab is you use a piece of styrofoam to go around your floor trap. That enables you to put in what's called a puddle flange, which is a deep flange to go around your pipework. That to me looks like a waffle pod slab. So we spoke about the waffle pod slabs earlier, how you just create a level site and you set out your styrofoam boxes and then you pour your concrete over the top. And we can see that there's lots of little squares happening in the top of that. So that's also indicative of a waffle pod slab. Once the concrete is placed, you have to take very good care of that. And one of the most important things you can do is enable that concrete to cure. So as soon as concrete gets mixed, you want to slow down that process of it drying out and going off. Yeah, an important consideration for where you get or who you buy your concrete from is how far away they are. You want your concrete batching to be as close to your site as possible, because it gives your concreters the most time to be working with that concrete in producing the slab. But then once it's all placed, all troweled and finished, you want to slow that moisture loss as much as possible. So several ways of doing that. One is to spray on a curing compound. So it's this blue stuff that gets sprayed on the top, and that stops the moisture coming out of your slab and keeps that moisture inside there and slows down that reaction. Another way is to cover it with plastic, or you can dam it up and cover it with water, or you can spray it with water. But basically what you want to do is you want to really slow down the moisture loss from that concrete. If concrete goes off really quickly and dries really quickly, it's much weaker because of the bonds between the molecules are not as not as thorough. So you want to slow down that moisture loss. So one thing you become very familiar with as drafters are footing beam details, typically. So if you work for an engineering firm, you'll be doing a lot of this stuff, but even in drafting, typical drafting practice. So this shows the cross section through a raft slab. So what we've got our ground level here. So that was that soil that we benched to. So we took off 150 millimeters of soil, and then we got down to this. Then we added 100 mil of compactable rubble and beveled those edges at a nice 45, and then put down our plastic, put our steel work in place in the cages, and then put up formwork and poured the concrete on top. There are a host of other details in terms of slabs and so on that you may look at. So these ones use separate bars. There's also stuff called trench mesh, which does the same job as bars, and in some situations you can supplement bars with trench mesh. Also, if we're going to be doing a core field concrete block wall, we'll typically concrete steelwork into that slab with a cog on the end to help tie the wall. So these sections I'll go through a little bit quicker. So what we've just seen, that's the mainstay of concrete slab construction in South Australia. But there are many other different types of footing systems to cater for many different situations. So one is the waffle pod, pier and beam, pier and slab, and that grillage raft that I spoke about. So waffle pod, developed by Kookaroo engineers. One of the big benefits of this is you don't require excavation or minimal excavation. You just bench the site. Very simple thing for owner builders to do. And then you set out these styrofoam boxes, and they've got little spaces that go in there that also hold the steel bars in place. So it makes it really simple for people to do. And then you set your edge boards around that and pour the concrete in there. You'll still need to have that engineered, of course. You're not going to come up, not design your own waffle pod slab, but you'll specify to your engineer, yeah, what we're wanting to do is a waffle pod slab, and then they'll specify what actual pods you need. If you're going to be doing wet areas or so, you obviously need those pods to be set down. One of the major benefits of that is that it has significant savings in concrete and steel. So the way that works, you need less concrete and steel for your surface area for your slab. So the process for that is removing the topsoil, lay all of your first fix plumbing, install termite treatment, place moisture barrier on the ground, and then lay out your styrofoam boxes. So that's how they come. So there's just stacks of styrofoam boxes, set them out with the right spacing, bar chairs on the top, and then you slab mesh on top of that. And then of course, after that, then there's the placing of the concrete on the top. As I mentioned before, we've got areas around Adelaide with really junky soil or things dumped in the ground that mean we can't simply do a slab on top. When we encounter situations like that, we've got to do a pier and slab. So that's where you auger out your piers to lock into stable soil down underneath, and then pour the slab on top. So once again, you clear the site, mark out positions of everything, bore the holes. Sometimes you'll need to place circular forms around the holes if you're picking those piers up. So something like former tube or something goes in there. Then, do I have any pictures of reinforcing cages? No. I'll quickly grab a picture of a pier reinforcing cage as well. It's the sort of thing I'm fairly sure once you see it, you go, oh yes, I've seen those before. So that's typically a pier going down into the ground. Those cages are made up above the ground and then lowered in. Fairly simple to make. So you just bend all your 10mm bar in a circle, lay your stronger bars in there, and then tie them at the right interval, and that cage goes in. And then the concrete goes around that. Once again, as with any concrete in the ground, you just want to ensure there's adequate concrete coverage to that. You don't want that cage laying against the dirt on one side. Because if it does, obviously it'll rust, explode the concrete away, and that pier won't last for long. So you bore out the holes, make your reinforcing cages, and then pump the concrete into the pier, vibrating that as you do so. Then once those are all set and gone off, you lay your underfloor plumbing and then pour your slab on top of those piers. And then finish your slab as you would with any other slab. Pier and beam, basically the same. So that can be timber beams or concrete beams. So that's typically for when you do piers that go out above the ground, and then you do beams across those piers, and then do the slab across that. So not all concrete slabs are on the ground. Sometimes you'll have concrete slabs set up above the ground as well. And when we get into project 2, we'll be looking at those type of systems, like what we have here. We have concrete slabs actually elevated for creating floors. Move on from that. Another thing about piers is those piers might actually be under-reamed as well, whereby you use your auger to cut out a cylinder in the soil, and then right at the base of that you have a tool which flares out and cuts soil out in a bell shape right at the bottom. That will enable concrete to go out in that bell shape and lock that pier into the ground, into that stable soil. The reason we want to do that is because if we've got a lot of surface movement, like soil movement at the surface, we might want to bypass all of that. We might want to lock into something stable down underneath and let that soil move up and down above it. If you're doing something like that, a really easy way of allowing that to happen is by getting some of that orange plastic, that same plastic that you use underneath the slab, and make cylinders of that, and make sleeves, and drop that down in your piers before you pour the concrete in, because it gives really smooth sides to your piers. That enables your pier to lock into the soil right at the base, but that soil can move up and down past it without influencing the side of your pier or your building. And that's an instance whereby you've got a concrete pad down the base of a pier. So I mentioned the grillage raft before. So the difference between your normal raft slab, which we spent a lot of time with, and your grillage raft is that rather than having 3 bars top, 3 bars bottom, and ligatures holding it all together in a cage, what you have is just 1 bar at the top and 1 bar at the bottom and these hangers in between them. So much simpler to fix. So it's a really quick process, and that's why volume builders like them. Because if you're just putting carpet over the top, well then it doesn't matter if you've got a little bit of cracking, a little bit of movement. And so there's definitely cost and time savings by doing grillage rafts like this.
Sorry, question.
Yeah.
Is that can be used for both 1 and 2 story buildings?
So yes, can be used for both 1 and 2 story buildings. Typically the big difference between 1 or 2 story building is weight. So any raft slab has to be designed to be able to carry the weight of the building. So if let's say for example we do a single story solid masonry house, that may actually be heavier than a 2-story frame and cladding house. So if we do a timber frame with weatherboard cladding on it and it's 2-story, that might still be a really lightweight construction in comparison to the house which is cavity brick. So your footings are going to be designed based on the weight that they're going to carry. So you can use a grillage raft for single story or double story for whatever weight you want to carry. That's going to be dictated by the depth of those beams and the size of the bars that go in there. Unfortunately we don't. In weeks to come, if we've got a little bit more spare time and the weather's good and there's still plenty of construction happening down here, we might be able to take a walk. There were last semester there were a lot of grillage rafts being built out in that Tonsley, that new subdivision area there as well. So hopefully we'll get to see some of those in practice. But basically, yeah, it's a deep narrow beam, and it may be a 2-pour process. So you pour all of your beams first, and then pour your top. The reason for that is because you've just got huge volumes of concrete going down into deep footings. Then with your strip footings, typically we don't use these in Adelaide because our soil is too reactive for it. But in scenarios whereby we've got fairly stable soil and we don't want to be spending a lot of money on footings and we're going to be using a timber floor, for example, then a strip footing might be a good alternative. Quite often also with
with strip footings, if it's going to be external walls, etc., you'll do it with concrete blocks associated. So, and one really handy thing with concrete blocks is you can core fill them. So you fill the cores, fill these holes in the centre with concrete. And if you carry reinforcing, so if you set reinforcing in that strip footing and carry that up, and then feed your concrete blocks on top of that reinforcing and mortar them in place, and then fill those with concrete, that binds that concrete block wall to your footing, which actually gives it a lot of strength. I did that for a retaining wall underneath a garage to hold a suspended slab. So fairly common example of where you would do a strip footing like that, concrete blocks on top, then to bear a slab on top. It actually gives a lot of strength because you can carry that reinforcing and bend it over and then into your slab as well, locking the whole thing together. So there's an instance there of a strip footing with concrete blocks on top, possibly core filled. And there's an instance there of a strip footing with your reinforcing sticking up. One thing you definitely have to do on site is cap all of your starter bars. Uncapped starter bars can actually be very dangerous. If you read the Safe Work SA on-site incident reports that come.
Fall on them or something.
Yeah, fall on them. Yeah, like a 10 mil rod. If you fall on it, it's so you've got little plastic caps go on top. Yeah, make sure they go on and go around. So yeah, once again, use string lines to set out for your footings. Place the formwork, and then finish your concrete to the right level. So nails or steel pegs are placed to indicate the finished concrete level. Typically, laser levels are ubiquitous these days. Concreters who use laser levels go around to get accurate measurements as they're setting out the concrete. And that's pretty much it for our concrete footing. So I'll stop that recording.